All right, guys, there we're going to stretch out our probability knowledge a little bit and do the addition rule. Sometimes when you're finding probabilities, you must add. All right, basically it's a tool for finding this, probability of A or B. And the key word here today is going to be or. The probability that either event A or event B occurs or both of them occur. That's what we're going to be working on today. It's called a compound event. A compound event is any event combining two or more simple events. Last week, all we did was work on simple events, like one event occurring at a time. Now we're going to put two together. Anytime in probability you see the word or, I shouldn't say anytime, but almost all the time, a great percentage of the time, it's going to mean to add. You always add when you see the word or. You're going to hear this about 75 times over the next 2 minutes in this video. You must avoid double counting. Do not count the same number twice. You cannot double count. You'll hear that again and again. All right. Problem here, if one subject, and you've seen this table before, if one subject is randomly selected from the 1,000 subjects given a drug test, find the probability of selecting a subject who has had a positive test or uses drugs. So that means they could have a positive test or they use drugs. So positive, this person is positive and uses drugs. This person is positive, this person uses drugs. That person. Those numbers are all involved there. So though everyone I circled, this one is really both. This one has a positive test result. This one uses drugs. So that's what it's asking. Positive test or uses drugs. I'm not really counting any of them twice. I'm just going to add those together, 44, 90, and 6. That's going to give me 140. So my probability is going to be 140 over all the people on the table, which was 1,000, which would be 0.140 for the probability. Now, keep that table in mind as we go to the next slide. Oh, I'll copy it again anyway. 3 ways to count that. Number 1 says this, color the cells representing subjects who tested positive or used drugs. That's what I did. I took my green marker a second ago and did this and this and this. I really kind of colored those 3. That's one way to me. That's probably the best way on this one. Number 2 says you could also do this right here. You could also add the 134 who tested positive. Like you could take these right here, take that whole column, to the 50 who used drugs. Like you could do that. Take that row, because that's the whole row, is people who use drugs and people who had a positive test result, and then just subtract out what you counted twice. Like if you look at that, if I do this column and that row, what happened was I counted the 44 twice. You'd have to subtract that out. So that's another way you could go there. And the last way it says that you can count is start with the 134. So start here again, and instead of adding the whole row, just add the 6 so that you avoid the double counting. So it's all about not counting the same number twice when you do your addition. All right. When finding the probability that event A occurs or event B occurs, find the total number of ways A can occur and the total number of ways B can occur, but find the total in such a way that no outcome is counted more than once. You can't count outcomes twice. You've got to find a way to do it without counting the same outcome more than once. Here's the formal rule, and here's how you're going to see it in problems in your book here. It's going to say probability of A or B happening, and when you see or, that automatically means you're going to do P of probability of A plus probability of B, but you're going to have to take out what they have in common. If they have outcomes in common, you have to subtract that out. So that's what this means. When you see probability of A and B, it's probably that they both can occur at the same time as an outcome of a trial or procedure. So this is what you're going to see a lot. And again, it avoids a double counting because you're subtracting out what you would double count. And this is more, the bottom red part down here is more of a everyday language of what that says. It says to find probability of A or B. Find the sum of the number of ways event A can occur, the number of ways event B can occur, adding in such a way that every outcome is counted only once. Have I said that enough yet? Probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. All right, so again, don't double count. Find a way to count, or if you do double count, make sure you subtract it out. All right. Events that are called disjoint or mutually exclusive will be your favorite kind today, because that means they don't have anything in common. If you read this sentence underneath it, Events are I put events are. That means they're disjoint or mutually exclusive. I'll be honest, most books use the word mutually exclusive, but disjoint is fine. And I think the author of your book likes disjoint better. Events are if they cannot occur at the same time. They do not overlap. Nothing overlaps. So I put an example down here. Example events that are disjoint or mutually exclusive. Randomly selecting someone who's a registered Democrat. Registered being the key word. Randomly selecting someone who's a registered Republican. Now, the selected person can't be both. So those are mutually exclusive or disjoint. And if you do probability with those, there's a good chance that you do not have to subtract because they're mutually exclusive. Example events that are not disjoint are not mutually exclusive. Randomly selecting someone taking a stats course and randomly selecting someone who's a female. That person can be both. You can be both a female and be in a stats course because we have several of them. So that's not disjoint or mutually exclusive. Disjoint means if you select like these top two, they have nothing in common. No outcomes in common in those two. These two, they do. You can do both. You can be both. All right, the Venn diagram of what they look like, kind of like these. Total area is 1 in that Venn diagram, and here's the deal. If they're disjoint or mutually exclusive, if you look at the Venn diagram, A here and B here have nothing in common. So no outcomes in common means they are disjoint. This is what disjoint that are not disjoint or not mutually exclusive look like. The circles have overlap because they do share some outcomes. In our last example, that'd be people taking stats and female. Those would be the stat class females in there. Okay, last thing. Complementary events in the addition rule. Reminder, we've talked about complements before. If you have two complements, if you do a reminder real quick, if you add up a probability of an event and its complement, it's always going to equal 1, always, because it's taken everything into account. So last week we worked on odds and stuff like that. If the probability of one thing happening was 1 out of 37, the probability of it not happening was 30. That's the complement, 36 out of 37. If you add those together, you get 1. That's all that is saying. Sorry, I stumbled across that quite a bit. So the rule is this. If you add the probability of an event and its complement, you get 1, which means if you're just finding the probability of a complement, you can do 1 minus the probability of the original event, and vice versa. The probability of an event is 1 minus the probability of its complement. Wow, that's a lot of words. Here's the Venn diagram for a complement. The probability of A is the yellow circle. If it's not in A, it's in blue. The blue section represents the complement, the probability of the complement, with the total area being 1. Anything not included in outcome A is then the complement, which is 1 minus everything in A. Hope that makes some sense. Let me show you one example. It's really easy. Last slide says, based on data from a Harris Interactive poll, the probability of randomly selecting someone who believes in the devil is 0.6. So, probability of believes in the devil equals 0.6. If a person is randomly selected, find the probability of getting someone who does not believe in the devil. So the word not automatically tells me I'm looking for the complement. So the way to find the complement is I'm just going to do 1 minus the probability that they do believe, right? That does believe. So that probability is in the problem, 0.6. So I'm just going to do 1 minus 0.6, which is 0.4, and there you have it. That's the probability that a person does not believe in the devil. So that's all I got for you today. Again, don't count twice. And that's going to be your challenge when you come to class tomorrow and we start working on these, is finding a way not to count the same probability more than once when you're doing these things. So look forward to seeing you. See you then.